Right. So in about 7.5 billion years, you will see a red giant, right? It will be like 1.2 astronomical units, right? The size of the sun. So 250 times of its current size, right? Now, as you know, 1.2 astronomical units means what? So the distance from the Earth to the sun is 1 astronomical unit, right? So this means uh, the size of the sun, right? This is radius, okay, is bigger than the distance from Earth to the sun, right? So this is like a Hollywood movie now, right? If you live that long, 7.5 billion years from now, and if you are on the Earth, if you try to fast forward all these things, you will see the sun. Now it's like small as you see it from the Earth, right? Uh, you will see sun is growing bigger and bigger and bigger, and it becomes more and more reddish, okay? Whereas now it is like yellowish. So the color turns from yellow to red, because red is like cooler than yellow, okay? So as the sun expands, it becomes little cooler. So the photons that are coming out of the sun is bit cooler. So therefore they become more reddish, okay, not yellowish. And the interesting thing is that you will see the sun in the day sky, right? And it's growing bigger and bigger and bigger. Initially, you see it like a very nice scenery, okay? Just like you see the sun as you go to the beach, setting sun, you look like bigger, right? It looks bigger than normal, something like that, something very similar to that. Now, but it's growing bigger, and you will feel scared at some point. My God, initially it was like a fancy story, beautiful scenery. Now it becomes a bit dangerous, okay, all of a sudden, because it is coming at you. Sun is coming to grab us eventually, okay? Sun is coming to swallow us. Sun will swallow the earth. And on the earth, you will see the whole earth is actually going into the sun. Okay, sun is so big, and the whole sky will be sun, just the sun, nothing but the sun, right? And we are inside the sun. So that is the end of the solar, the earth anyway, right? So when that happens, sun's surface would be much cooler, about 2600 Kelvin, right? Now you might laugh, right, when I say it's cooler and temperature is 2600 Kelvin. So this is astronomical units and all, right? Usually sun is much hotter, the surface, right? It's not 2600. So uh, so as the sun expands, its temperature drops to about 2600 Kelvin. But the luminosity increases up to 2700 times current solar luminosity. Luminosity is basically the amount of light that it gives out, right? Now, because sun is now bigger, you get more luminosity, okay, for the same energy, right? Because now it's bigger. But the temperature is lower, 2600. So sun will have a strong stellar wind, which will carry away around 33% of its mass. So remember this one? As I explained, when the sun is burning hydrogen very close to the surface, the remaining portion of the surface, or from the surface to the hydrogen burning layer, it will be not that strong to hold the whole thing, because of the burning hydrogen and the expansion. This outer layer will be expanded out from the sun, and that matter will not return back to the sun, it will go away. So that is a mass loss, right? According to the models, at present, this mass loss is about 33%. Again, these numbers will change. Don't worry whether it is 33 or 35 or 25, right? Anywhere around that figure. So as the sun expands, now this red giant stage continues, but it will not continue indefinitely. There's a limit for that, because the whole thing is physics based, right? When one variable goes beyond a certain level, that progression itself tries to turn it back. Okay, so that is how things are connected naturally. It will most likely swallow the planets Mercury and Venus. Earth's fate is less clear, but 2008 studies suggest that Earth will likely be swallowed. So as recent as 2008, we have some more confident data that the Earth will also be swallowed by the sun. Okay. Now what? So hydrogen burning in the shell around the solar core will increase the mass of the core until it reaches about 45% of the present solar mass, right? So there's a solar mass at the core, that is hydrogen burning core, and actually at the core it is ashes, that is helium. This amount will grow into about 45% of the present solar mass. So nearly half of the sun would be helium. Okay, so as you burn hydrogen, you get more helium. So as you get more helium, there's a structural change in the sun. The helium is in the center of the sun, so it becomes more and more dense core. Okay, so at which point the density and temperature will become so high, you can expect that to happen. Helium is so heavy than heavier than hydrogen, and when you have a lot of helium in the core, it is highly compressed area, so that more you get more heat there, pressure, heat, and it will start giving rise to what is called helium flash. So it will start burning helium into carbon. So that is another nuclear chain reaction. The first one, the simplest one, is hydrogen to helium. Then you have helium to carbon. Helium goes through a complicated nuclear fusion process and into carbon. Then now you have actual ash. Carbon means like ash, right? Real ash, like on Earth. The sun will shrink from 250 to 11 times its present radius, because this contraction, right? Its luminosity will decrease 2700 to about 54, because now you don't have a lot of heat, because no hydrogen burning. What you have is helium burning, but it's at the center, it's at the core, right? So it will take many years to come to the front, to the surface rather. So if you look at the surface temperature, will increase to about 2600. So from 2000 to 4770 Kelvin. So you get some sort of heat on the surface. Luminosity drops, but it's kind of hot. So the sun will keep burning helium in its core in a stable fashion, much like it burns hydrogen today. So then you get another stable phase. of sun burning now helium, okay, not hydrogen. The helium fusing stage will last only 100 million years. Not like hydrogen, this is fast burning, so it will not last more than 100 million years. As the core depletes with helium, the sun will burn the reserves of hydrogen and helium in its outer layers and will expand for a second time. So from this point onwards, nothing is really certain because it's a very complicated structure in the sun. You have helium in the core, helium burning shell, some hydrogen on the outer surface, like that, right? It's like bushfire, right? The fire here and there, nobody knows exactly what's going to happen. Right. So eventually, sun will deplete of the energy. No helium, no hydrogen. It will be carbon core. It will be carbon core. Over the course of a further 100,000 years, the sun's remaining outer layers will fall away, right? Like that, ejecting a vast stream of matter into space, forming a halo, misleadingly known as planetary nebula. So like this is what I said. We have seen photos of um, other parts of the universe where you can see nebulas like this. So this is probably a dying solar system, who knows? Or at least a dying star, right, at the center. And when it depletes of hydrogen and burning takes place at the near the surface, it blows away some material just like this. So we can see our fate, we can see our future, like future today, right? You can see around, you can figure out what's going to happen to you. Like when you see a elderly person suffering from some disease, that maybe that's your future. Okay, you see that. You don't have to wait until it happens to you. You can figure out, I'm also a human being and he's also a human being, and he's 20, 30, 40 years elder, right? Now this is the fate I'm going to have, right, when I come to that stage, something like that. In astronomy, this is the scientific process. We can't wait these astronomically long time scales to see things, what's going to happen to Earth, solar system, etc. Instead, what we do is we take photos, we do observations, what's around us. There are small stars, big stars, old stars, young stars, than the sun. So you can take these photos and put them together and start telling the story. This is how the stars are born, this is how they live their life, this is how they're going to end their life, right? Very much the same process. So then you have the theories, the physics, etc., to stitch them together more tightly in a scientific manner, right? So you explain the observations using theory, right? Or refine the theory using observations. It happens both ways. That's how science develops, right? So sun's loss of mass. So about 30 or 1/3 of the mass, right, is going to be lost forever, and could send the orbits of the surviving planets into chaos. At that point, Earth loses the gravity. Sorry, the sun loses its gravity, right? Orbits are held in their positions because of the gravity of the sun. So the moment the sun loses the mass, it blows out, right, the mass. It will go far away, right, beyond the solar system, maybe like small matter, right? Then sun is not enough, not big enough, not heavy enough to hold the planetary system. Okay, so then the planets will go away. Yeah, like a family with a father, right? He keeps things going. Okay, and every other member of the family, they stay around the father, right? The moment he's not there, right, there's no central controller to keep things intact. So the others will also fall apart. It happens to the governments also. When you don't have the prime minister or the president in place, the entire group that was around those people will shatter. The network will shatter, and they will become individuals, and they take decisions individually and not with any synchronization with them, as they used to do when the leader was there. So same thing happens here, right? So you can see a lot of analogy, right, of astronomy being repeated in other fields also. So that's why I really like this subject. You can learn a lot of things just by following these processes, right? Uh, it is a huge amount of knowledge and experience. So afterwards, all that will remain of the sun is a white dwarf. We first time give the sun the name dwarf. Dwarf means very small, right? It is a white dwarf because even though it's very small, it has a lot of energy, heat, still glowing. It's glowing like a white ball, okay? But it's extraordinarily dense. It's about 54% original mass, but a very small size now. Size of the Earth, my God. This is half of the sun, right? In half of the sun now, in a size of the Earth object. Okay, so you can imagine how dense that would be, right? Now this energy dissipation is happening all the time, right? Therefore, this white dwarf will gradually become a black dwarf, right? Before that, it becomes a brown dwarf, black dwarf, and it will glow dimmer and dimmer, right? As it depletes energy, and it becomes invisible eventually, right? It becomes black dwarf. So at that time, you don't have to worry about the solar system. There's no such thing like solar system. Planets are here and there, right? It becomes like debris. It's a graveyard. Okay. So the remaining mass of the sun, now we call it a black dwarf. It doesn't have energy. All the energy has been dissipated in the form of radiation. Now it's a very, very cool body, a very cold body, right? Carbon and oxygen, primarily carbon and oxygen in there. And the core will freeze. It will be a crystal kind of thing. It will be a very big crystal ball. Who knows this? When you have carbon in a very highly dense form, it might become like diamond. Diamond is very precious, but if you look at the universe, uh, we don't value anything over anything else. They all matter, right? Hydrogen, helium, water, diamond. There are huge amounts here and there, various places, and there's no value for that. Okay, they are all equal. So in the universe, you have all these things. Like for example, gold. I think I explained you that in the first lecture, how you got gold, right? And in this discussion, there's no gold, right? It's like carbon, oxygen, and you can go up to about iron, right? Inside a sun. But beyond that, gold, platinum, etc., sun cannot produce anything. But here on the earth, you have gold, right? And some people think that gold is actually formed inside the sun. No. How can we make gold? You can't make gold. To make gold, there should be a nuclear reaction to bring other lighter material into gold. That you can't make it in a factory, right? It has to happen in a very dense, a very hot environment, like a burning star or core of a star. Core of a star. Now all these carbon and hydrogen are happening because of helium fusion in the core of the sun. Okay, you can't generate carbon or helium anywhere else. What is abundantly available in the universe is only hydrogen, not even helium, right? Only a natural thing that scientists have figured out that you can have without any production process is only hydrogen. So everything else were made out of hydrogen. Hydrogen fusion produce helium, helium fusion produces carbon, oxygen, other things. Then it goes on and on and on. If you want to generate heavier material like iron, platinum, gold, etc., it has to happen in a much bigger star, bigger than the sun. Okay, so that's how we got all the heavy materials like iron, like gold, for example. So you are wearing gold, right? They came from stars. Do you believe that? Billions of years ago, not in our lifetime. This matter is much older than all of us. Okay, billions of years old, and a star exploded, a much bigger star, and then it got all the material, like including gold, out to the interstellar medium, like explosion of a bomb that will shatter everything. Okay, the matter goes everywhere, like that, highly irregular. And after that, this sun was so big, maybe million times bigger than the sun. And then the debris field, after another maybe billion years, right, started to contract again, a small portion of that. And it eventually gave rise to a star, our sun, and the planets. So actually we became, okay, before the sun and the planets, this place would have been a graveyard, okay, of a much bigger star. So that is more logical explanation. Where we are today, sun and the planets, was a graveyard of a much bigger star. Okay, maybe some 10 billion years ago. That star, whatever it is, let's say X, the star X, million times bigger than the sun, exploded and created gold and other material, uranium, thorium, plutonium, platinum, etc. Right? And then this is million times bigger than the sun. And in one corner, right, after about 4 billion years from that incident, right, that area started contracting again, and it gave birth to the sun and the planets. So from that point onwards, now we are halfway, like 6 billion years. Okay. Now that some of this gold is here now on the earth, because the earth was formed out of the debris of the graveyard. Okay. And it had some little amount of gold, and we can see it here on the earth. So that's the story. All right. So any questions of that, please? All right. So now I'm gonna show you a little video of all these things, because if I explain everything as clearly as I can, still it's good to see something, right? It's good to see. Let's let me pick up one of the things here. End of solar system. Let's do. Let's see this one. Right. Can you see my screen? Can you see the video? Yes, sir.
Yes, sir.
Yes, sir.
If you cannot hear the sounds, let me know. So this is a journey from the Earth to the outer space, right? So we start from a car park, right? This is the car park. You can see it very close to the surface of the Earth. And now we are moving outward. So now you can't see the car park anymore, but you can see the buildings, roads. And now you can't see individual structures, but you can see the towns and all, right? Highways, big structures, right? Now you can see probably the countries, right? Regions. Now the continents. Now you can't see even different countries. Right? It's part of the US now, like in New York area. Now is the whole Earth, right? And now you are in space, and you can see the Earth and the Sun and the other planets. But remember, this is not the reality. You can't see the Sun and the planets like this. Okay, you can't have planets this close to the Sun. This is only artistic illustration, not the reality again. I think you remember the scale model of the solar system. There you figured out the enormous distance, right, between the Sun and the planets. All right, now it's about the size. So this is Pluto. About 2,000 kilometers in diameter. Then you have Mercury and Mars together with Pluto. Then Venus and Earth. Now you immediately see these are the inner solar system planets, right? Except for this guy, Pluto. Now see Earth, Venus, Mars, and Mercury, right? They are comparable in size, right? Comparable in size. But this guy doesn't match, right? Pluto. Pluto is extremely small. So this is another reason as to why we have doubts considering Pluto as one of the members of the solar system. But I have to tell you this, it's not very rational. So this is not the rational way of taking decisions, right? Okay, we see, okay, these guys are big, this guy is small, or we want to separate these things out. Now, there should be some physical or scientific basis for that. Okay, just because this is small or just because it is black or white or whatever, you cannot discriminate, right? That's not correct. But there's a scientific truth behind that also, right? I'm explaining what you see in evidence. Then you get the outer solar system. You can see they're very big, right? Neptune, Uranus, and Saturn and Jupiter. Now, again, you can see there's a lot of similarities, right? These two guys are somewhat like they're coming like in pairs. Jupiter and Saturn as a pair, Uranus, Neptune as a pair, and Mars and Earth like a pair. I don't know whether there's something going on in here, right? So it's good to be a bit curious and ask questions. Is there anything happening here, right? Why are they not like random? Okay. So why such a coincidence, right? Then the big guy, sun. Now see, there's no match, right? You compare the sun with the planets, it's no match. So until you see this kind of scale structure, you don't really understand the reality. You can read books, you can listen to lectures, but still it's incomplete knowledge. Okay, and people cannot actually conceive the reality uh, just by thinking and looking at the numbers. You have to see it for yourself. So it's not the end of the story, though. There are other stars. Sirius. Sirius is the brightest star in the sky. You can see it time to time, right? Some of these stars, please take a note of these names, right? All of these stars are bigger stars. I'm going to show you, right? You can see a map, star map, and figure out where they are just to have a look and remember some of the names of the stars. It's a good thing, right? It's a good thing to say that you know some of the stars, right? At least this astronomical stars. If you don't know other stars, movie stars, etc., you can say, I know other stars in the sky, right? Sirius, brightest star. It's so bright, you can see it's white color. White means bright, okay? What about Vega? Vega is also visible star. Pollux. Castor and Pollux are the two stars in the Gemini. And Arcturus, Aldebaran is in, I think, area. In which constellation is Aldebaran? Aldebaran is, I think, in. Does anybody know about Aldebaran? Which is the constellation Aldebaran is in? Is a red giant star. I think it's Aries. Let me check. Regal, Deneb. Now you can't even see the sun, right? This is the astronomical scale. The scale is so wide, there's no way to compare these things. So therefore, some of the things are invisible when you talk about something else. When you talk about Deneb and Rigel and big stars, the sun and the solar system is essentially invisible. There's no discussion. It's not a factor. It's not a variable in the discussion. Okay. Then the pistol star, Betelgeuse. Betelgeuse is a very bright star, in red giant star. You can see Betelgeuse in the nebula Orion, right? Orion is a very famous, most famous constellation. You need to see that. Probably Shakya will come and talk to you about night sky and observation. Then he will talk about Orion and Betelgeuse. Antares, VV Cepheid. Right. Then I want to show you this one also. So this is the end of the solar system, as you can see, right? 5-6 billion years from now, right? All what I explained to you in a cinematic manner, right? This is when is running low on hydrogen. You will see inner core is basically helium, and hydrogen burning is happening the outer shell, and it expand the sun. So some of the planets will be swallowed by the sun. So it puffs off matter from the surface in an oscillatory manner, right? And it loses energy, loses matter. Eventually, this is what remains at the center, the dense core. But all the matter that you saw earlier as a big star is actually gaseous matter. It's not solid matter, gaseous matter. So when the sun puffs off this matter, then you see actually the dense core is this much. Okay, it was like a camouflage, and somebody looks like a very big guy, but eventually when you go in there, you will see there's nothing in, right? It's a small chunk. It's all cosmetic camouflage. So this is what is actually inside the sun, a dense core. So around that core, now all of the matter is now in the periphery, right? Like a graveyard. It forms another nebula, like what it came from, right? Uh, uh, the same destiny. So nebula gives birth to a star, and the star gives birth to a nebula. It goes like that. So if Mars survives that long, it will be the closest planet to the black dwarf. Closest planet to the black dwarf. So if you want to make a choice, right, where is our next destination? Probably I will pick up Mars. So we have to colonize Mars, build spacecrafts to get from Earth to the Mars, and build colonies there, how to live without the sun, how to get energy without the sun, right? When the technology is developed to that level, right, probably this will be our home. The long behold, we will be living on planet Mars. It's not a fancy dream, very much the reality if we survive that long. right? We have 4 billion years from now to do that. Is a huge, long time scale. And well before that, I think people will colonize Mars, not in our lifetime, right? But in probably within a million year, 100,000 years from now, right? Probably Mars will get colonized. And on the other hand, the flip side of the story is that before the sun, right, explodes and swallow all the planets, probably some bad mistakes of the humans on the Earth probably will terminate the entire life of the Earth. Okay, if that happens, right, there's no point of talking about going from Earth to the Mars and colonize it there. We will cut short our evolution, right? Because very much so, the way people are um, uh, living on the Earth, how badly they destruct the environment, how negligent they are for the ecosystem, the carbon footprint, green percentage, ozone layer, and salinity of water, that kind of thing, right? Because these things are intertwined very intimately, right? When you take these factors and try to harm one of the factors too much, it will affect the other factors also, because they're so tightly, intimately intertwined, right? So then the whole thing will collapse at some point. So when it gets to that point, the environmental instability, right? Say, for example, temperature of the sea water, right? If you destabilize that, if you destabilize the glaciers, it will not be easy to uh, turn that back. It will not be a cabinet decision. Okay, it's not a decision to be taken by the parliament, right? When the whole nature turns against us, nobody will be able to stand against that. So when that happens, we just have to wait and face the bad destiny. So that is very much a reality, because there are a lot of people who don't understand this one, but running the countries, continents, just looking at their own territory, they don't understand the global picture. So their bad mistakes will make us suffer. So it's happening in the small scale, in the regional scale, the global scale also. So one of the major objectives of this module is to make you guys aware of these things, right? Even though we are talking about astronomy, the objective is to make a change here on the Earth, right, to positive side. So because they're all connected. Right, so that's end of that lecture. Any questions about that? In that case, let's take a little break of 10 minutes. Okay, welcome back. So second lecture is a bit different. I think it's more fun in terms of the calculations and measurements, right? The title is Measuring Stars. So we are going to measure stars, okay? This will be definitely a very different experience to you. So you have been measuring things all this long, right? And objects that you can see, right? And touch and feel. But have you ever tried to measure stars? No. We are going to do it now. So let's see how. What is there to be measured, right? First thing is the distance, right? Uh, Now let's see, let's look at this uh, graphical illustration here, right? There are two people here, position A, position B, and there's a nearby tree, right? And you see the tree top. If you ask from the person at position A, right, uh, where the tree is aligned with, and he would tell that the tree is aligned with this mountain, the right one, right, rightmost mountain peak. He would say, now if we give three names, mountain 1, 2, and 3, right? Position A observer, he would tell you that the tree top is aligned with mountain mountain 3 top. Okay, the peak of the mountain 3. And if you ask from person at position B, he would tell no, the tree is aligned with uh, mountain 1 peak, mountain 1 peak. So at the same time, they tell you two different observations. Okay, so how can you see the same object, right, as aligned with two different positions with respect to the background, right, at the same time? The only only way that this could happen is that the object that you are trying to measure, that is the tree, right, is not part of the background, but it's close by to you. Okay, when the tree is closer to you, you will see this difference. So closer the tree to you, the bigger this difference is, right? Now, if you take this to astronomical scales, right, you will see some similarity, like over here. Rather than having two people, person 1, person A, and person B, right, this is the position of the Earth at two time stamps, right? When the Earth is over here and when the Earth is over here, like the two people here, A and B. So you take a photograph of this nearby star when we are here, and you will see that particular star, right, which is a nearby star, not the distant stars. So by the way, there are distant stars and nearby stars. Remember that, okay? Distant stars are much farther away at infinity, okay, at infinity. But there are other objects nearby going around us. So we are going to measure those objects, right? Not the stars at infinity. Um, so, uh, so you will see when the Earth is over here that the nearby star is aligned against this area of the background stars. Okay, so these are background stars, and whenever or wherever you take photos, you will see the same structure because they are at infinity. They are at infinity. They are all moving at different directions, very high speeds. But if you look at their distance from here, right, their relative motion is negligible. Okay, relative motion is negligible. If you take a photo and you take another photo after 1,000 years, you will still see pretty much the same positions, right? But the nearby star, if you take a photo after 6 months, right, because the Earth takes 6 months to get from this point to that point, to complete one half cycle of the orbit, and then you turn back to the same star, take another photo, and this time you see that star against somewhere here, this background star. So there's an apparent movement from here to here, right? Apparent movement from here to here. So if you draw say if I draw it, so if this is my photograph and the background stars are say like this, these are my background stars, These are my background stars, right? I see the nearby star, right? Somewhere over here, I draw it a bit bigger because it's a brighter star, nearby star, right? Oops, what happened? Right. So I see it in the first photo somewhere over here, right? And in the second photo, after 6 months, I see it maybe over here, right? So you can measure the angle from here to here, right? What is this angle? This relative motion of the nearby star is because it is nearby and because of Earth's motion, right? So if you measure this angle and divide by 2, right, that half angle would be the parallax angle. Now you do simple math. This is 1 astronomical units, right? 150 million kilometers. And this is, say, in arc seconds, right? You know, arc seconds, 1 degree, if you divide into 60, it's a minute. And then you divide further 60 arc second, right? It goes like that. So, you know, the trigonometry here, r theta is the distance, right? R theta is the distance, and it's P here, RP is the distance. If you know, this distance is 1 astronomical unit, and this is probably R, right? Then you can calculate R if you divide distance by the parallax angle in radians. Okay, so in radians, this is a very, very, very small angle. When you divide 1 astronomical unit by a very small number, you get this big distance, right? Long distance. Now, if you try this technique to measure distance to a farther away star, somewhere over here, right? Angle is small, but if it's a nearby one, you get a bigger parallax angle, okay? Now, there's a limit that you can measure with some certainty. So when you try this technique for stars farther and farther away, you will start to see this angle getting smaller and smaller. And beyond a certain small angle, there's no point of measuring it anymore because the measurement error would be so big. Okay, so therefore you can't use this technique for any star, but only for nearby stars. So nearer the star, higher is the accuracy. Now this is the equation, very simple equation. As I said to you, D equals 1 over P, right? This comes from the equation R theta, right? If you have a right, this is arc length, this is R, right? This is the angle P. What is this arc length? If you take this as S, so S equals R theta, the theta is P, right? When P is very small, when P goes to 0, right? You know that. You can say this S, right? Or R rather, can be calculated S over P, right? So this is a very small number, right? Nearly 0. S is 1 astronomical unit, 1 AU, it is actually not the arc length. When p goes to 0, it is a straight line. That is the radius of the Earth's orbit. Okay. So now the beauty is, if you put one arc second, right? If you put 1 arc second for p, right, 1 arc second, and this is 1 astronomical unit, you can calculate the distance, and that distance is called parsec. That distance is called parsec, right? So it's about 3.26 light years, because in this equation, if you know 2 parameters, you can calculate the other one. 1 astronomical unit for s, and 1 arc second for p. The distance, whatever you get, right, you call it parsec. And when you turn it to other units of distance, like for example light years, it will be 3.26 light years. Okay. So all non-stars have parallax angles less than 1 arc second. Because why? Why don't we have stars with bigger parallax angles? Because the stars are farther away from us, right? Because stars are not very abundant in a nearby area, right? To find a star, you have to go a long way from here. And most of the stars, right, the parsec, the angle is less than 1 arc second. Less than 1 arc second. Meaning the distance more than 1 parsec. So the distance to a nearby star which has a parallax angle 1 arc second is 1 parsec, right? 3.26 light years. But all the stars that we see are farther away, right? More than 3.26 light years. So which means the parallax angles of all these known stars are less than 1 arc second. 1 arc second. Okay. And as I explained to you, you can't extend this method for all the stars, because as you go further and further, the angle becomes very small. So then you find it difficult to measure with certain accuracy. So therefore, the limit is like few hundred parsecs. You can use this technique for few hundred parsecs, all the stars in that area. Beyond that, you can't use this technique. Now, take a piece of paper. So I want to make it a bit more interesting to you, right? And for the moment, you become an astrophysicist, right? Working on stars. Take a piece of paper, all of you, and try to work this out. The closest star, as everybody knows, is Proxima Centauri, right? The closest star, Proxima Centauri, has a parallax angle. You know that? 0.772 arc seconds. I just mentioned that all the stars that you see in the nearby area, right, they have parallax angles less than 1 arc second. Actually, the closest one, right, which is having the biggest parallax angle, okay, is Proxima Centauri, and the parallax angle of Proxima Centauri is 0.772 arc seconds. Now, can you get me this answer? How far is Proxima Centauri from the Earth? Please do the math. Quickly do that. Okay. So can I get you answers? We have Nachib 1.295 parsec. We have Delogen 4.223 light years. Any other answers? 1.295, I think, parsec, right? So now it doesn't matter, right? Now this is your first calculation of a distance to a star. So I think it's a historical day in your life, right? You can remember this date that you calculated the distance to Proxima Centauri. Okay. So others, can you raise your hands? Those of you who have tried. Can you raise your hands, please? Those who have tried this small sum. I know 3 people have tried. Can you raise your hands? I just want to get a number and whether you are actually interacting with this process. So we have 14, 16, 19. But more than half have not tried even, right? More than half haven't tried. Can I ask Vijayaratna SH? Vijayaratna SH. Have you tried? Vijayaratna SH, are you there? Vijayaratna SH. Are you there or are you not there? Surabhige? Surabhige, are you there or not? I want you to turn your videos on for a moment because it's not good. I don't think people are there because even though I see the names, I don't see many people are there. Can you turn on your videos, please? Can you turn on your videos, please? Please, because if I don't see people actively engaging, then what's the point of having the lectures? You don't have to worry about how you look like. I don't mind. Just turn on. Ilanga Singh, Karyavasam, Abhesekara, Pabadita, Yapa, Malshika, Udayanga, Vikramarachi. Are you guys there? Tamudita, Netmini, Silva KDC, Deniyegoda, right. So I think I have got more than 50 now, 50%, right? Okay, you can turn off now your video to save your bandwidth. I don't want to consume your bandwidth, but maybe we need to get some sort of attendance next time onwards. Right. Okay. So this is the answer. D equals 1 over P. Very simple. D is the distance to the star, 1 over 0.772 arc seconds, right? So this one means astronomical units, right? 150 million kilometers. And then when you divide, uh, uh, it becomes the parallax angle is 0.773, right? When you substitute it, it will be like 4.24 light years. The closest star is 4.24 light years. I think you remember this, right? How far away is the closest star, right? You read it from books, right? And like four light years, remember? So this is how that number comes from, right? The parsec calculation, 4.24 light years. Okay, so next, what else are we going to measure? So we are going to measure stars, right? So the other things we are going to measure is luminosity and brightness, right? So we are going to measure the distance to the stars, luminosity, brightness, that kind of things. So it's going to be very interesting. Now, by the way, what time is it? Oh, it's 7:05. Right. Okay, fine. So I think that out of time for today, we can't, we don't have time to start this new topic, luminosity and brightness. So I'll leave it for next week. All right, then. Any questions up to that point? Okay, some have got power cards. Fine. Right. Okay, then. So we'll stop for the day and I'll see you next week.